Hi, my name is Johannes. I'm happy to present our paper Breaking Symmetries with RootClique and LexTopsort, which is joint work with Markus and Stefan from Vienna. Let's right start with the motivation. Fractional Hypertree Width is a combinatorial measure that renders CSP as well as sharp CSP tractable. More precisely, it makes instances solvable in time polynomial of the instance size and exponential of the fractional Hypertree Width. It's the most general known structural restriction that guarantees polynomial time solvability of CSP, and in particular it is more general than Treewidth. Recent works have considered the computation of the measure, and one approach formulates an SMT encoding, so satisfiability modular theories, that determines the width and provides a practical implementation called FRA-SMT. Another approach implements a combinatorial algorithm into a solver called triangulator, and a latest version called Triangulator MSC. The solver is quite successful in many hypergraphs and solves most of the instances quite fast. The success of Triangulator drove us to the question whether one can improve the SMT approach further. A classical approach for combinatorial solving is then to use symmetry breaking. And that is the focus of this paper. Why can symmetry breaking be particularly interesting? Fractional Hypertree Width is defined in terms of an unrooted decomposition tree. The core of the SMT-based encoding is an ordering-based characterization of fractional Hypertree Width. A hypergraph with n vertices has n factorial linear elimination orderings, and many correspond to the same decomposition tree. In consequence, it seems obvious that there is much room for symmetry breaking strategies. Then our immediate research questions are: can we apply symmetry breaking to the SMT-based approach for finding fractional hypertree decompositions and hence the fractional hypertree width? Are there different versions of symmetry breaking techniques possible, and what are the potential effects? For example, if we have a static symmetry breaking technique that is pre-computed in the beginning, or a dynamic one that is part of the encoding. Before I go into the details, let me quickly summarize our contributions. We speed up the SMT approach for finding optimal fractional hypertree decompositions. We introduce and study two new symmetry breaking methods, and overall we investigate a dynamic and a static version of RootClique and LexTopsort. I'll explain in a bit what this actually means. Now for those who are still interested and want to see more of the talk. Let me first fix the background and introduce you to fractional hypertree width. Probably many of you have heard about Treewidth or bucket elimination and induced width. Assume that the hypergraph on the left-hand side is a constrained hypergraph of a CSP instance consisting of 8 vertices and 5 hyperedges. Okay, Treewidth itself is defined in terms of tree decompositions. A tree decomposition is a tree whose nodes are labeled by bags, and a bag consists of a subset of the vertices. The tree decomposition has to satisfy two properties, namely every hyperedge is fully included in a bag, and all bags that contain the same vertex are connected. The width of a tree decomposition is then the size of its largest bag minus 1 for some arbitrary technical reasons. In our case, the width of the tree decomposition is 3. The tree width then is the minimum over all possible tree decompositions. Fractional hypertree width generalizes this concept. On top of simply considering the number of vertices in a bag, one defines a so-called fractional edge cover, where one assigns for every bag and each of its hyperedges a value between 0 and 1. In our case, the hyperedge that contains v1, v3, v5 is assigned a 0.5. The one that contains v1 and v2 is assigned a 0.5, and the one that contains v2, v3, and v5 also is assigned a 0.5. Then we simply require that covering vertices in a bag is ensured by the fractional edge cover, meaning that we sum over hyperedges of the bag in which the vertex occurs and the value for the fractional edge cover. Then the sum has to be larger than 1. The width then is the weight of the largest fractional edge cover needed to cover a bag, which is 1.5 in our case here. Then the fractional hypertree width is the smallest width of all fractional hypertree decompositions. Induced fractional hypertree decompositions are similar, but based on the definition of a successor on hypergraphs. And the fractional hypertree width of a hypergraph equals the smallest fractional width over all its linear orderings. The illustration on the following slides makes it a bit more visual. The SMT encoding is based on a characterization of fractional hypertree width in terms of linear elimination orderings of the vertices of the decomposed constraint hypergraph. One by one, we delete vertices that appear only in a leaf bag, then delete bags that are contained in their parent bag. Let's consider another hypergraph on the left-hand side and a decomposition on the right-hand side. F is only contained in a leaf bag, so delete F. The bag that now contains A and G is entirely contained in its parent bag, so delete the bag. A is only contained in a leaf bag, so delete A. The bag that contains C and G is entirely contained in the bag that contains C, G, and H, so delete the bag C, G. E is only contained in a leaf bag, so delete E. The bag that contains G and H is entirely contained in the bag C, G, H, so delete the bag that contains G and H. G is entirely contained in a leaf bag, so delete G. The bag that now contains C and H is entirely contained in its parent bag, so delete the bag. D is only contained in a leaf bag, so delete D. The bag that now only contains C is entirely contained in its parent bag, so delete the bag. C is contained only in a leaf bag, so delete C. H is contained only in a leaf bag, so delete H. B is contained only in a leaf bag, so delete B. When we consider the primal graph, it contains an edge between two vertices whenever they appear together in a hyperedge, so it's static and independent of the decomposition. The induced graph contains in addition fill-in edges, is dynamic and independent of the decomposition. The SMT approach takes the ordering-based characterization and encodes this into an SMT encoding, where we have clauses for transitivity of the ordering, clauses for the induced edges, similar to Treewidth, and arithmetic constraints for the fractional edge covers that are encoded in SMT. However, the SMT encoding has a major issue. The solution space is quite large and it allows many symmetries. Hence, we aim for symmetry breaking for elimination orderings.
Take a look on an overview of our considered symmetry breaking variants. With symmetry breaking, predicates have a static and a dynamic version. First version works on the primal graph and can hence be computed in advance. Therefore, we call it static. Second version works on the induced graphs by adding predicates to the encoding and is computed during the search. We therefore call it dynamic. Consider RootClique and LexTopsort. I will provide you with the definitions in a sec. Static RootClique predicate has already been described and works by Boatland and others, and we used the version in our CP2018 paper. Introduce new variants of static RootClique. Introduce and implement dynamic LexTopsort for fractional hypertree decompositions. Introduce static LexTopsort. Dynamic LexTopsort has been introduced by Andre Schiedler and Stefan in their 2019 LNX paper for hypertree decompositions. We implement dynamic LexTopsort for fractional hypertree decompositions. Slides before I explained you the topological sorting and that we can obtain it by repeatedly deleting vertices without incoming arcs until all vertices have been deleted. This provides us with the obvious ways for symmetry breaking. We fix the root and introduce a topological sorting to determine the linear ordering uniquely. We call the resulting two symmetry breaking predicates RootClique, since we can simply choose any clique in the primal graph to fix the root, and LexTopsort, as we can uniquely determine the linear ordering by lexicographically sorting. Since the clique may appear anyways in different bags, we're not breaking all symmetries here. In order to maximize the effect of the symmetry breaking, we consider various strategies to obtain the best results. So first we simply take the size of the clique plus its neighborhood in the primal graph, and then the size of the clique minus its twins, and then simply considering the number of hyperedges that are incident to the vertex of the clique. Topsort is quite effective in terms of symmetry breaking. However, the predicate encoding is quite expensive. Hence, we provide a relaxed static version. The static version does not break all symmetries, but is significantly more compact. Now let's take a quick look on our symmetry breaking predicates and how we implement them. For the static RootClique predicate, we implement the different variants for choosing the cliques in the primal graph. Those are computed beforehand, and then the clique is inserted into the encoding. For the dynamic RootClique predicate, we implement this directly into an SMT encoding that is cubic in size. There we aim for a largest bag of the resulting decomposition to be the root, and the clique is in the induced primal graph. Static LexTopsort, we introduce a lexicographic sorting of the vertices on the primal graph. For the dynamic LexTopsort, we introduce a lexicographic sorting of the vertices on the induced primal graph. If we want to use RootClique and LexTopsort together, we have to take care that the ordering is in line with the vertices of the RootClique being the lexicographically first. Have a look on the setup and the outcome of our experimental work. Used the benchmark set HTD bench that consists of 2191 hypergraphs, some CSP and conjunctive database queries, and the hypergraphs have up to 2993 vertices and 2958 hyperedges. The set has been collected by Wolfgang Fichte together with Georg Gottlob and Reinhard Pichler, and it's developing over time. So it's kind of a dynamic setup where people can upload hypergraphs. Since this is a bit of a problem for a benchmark setting, the hypergraphs are also available online on Zenodo, which we exactly took for the benchmark setting. Our experimental setup then consisted of a cluster running Int'l Xeon CPUs where hyperthreading has been disabled. We used a timeout of 7,200 seconds and limited the available RAM to our SMT approach to 8 GB per instance and 64 GB for triangulator, since it turned out to be quite memory demanding. Let's take a look on the results. Here you can see a plot, a so-called cactus plot that illustrates the asymptotic runtime behavior of programs. The cactus plots are still popular in the SAT and SMT community, but if you haven't seen it before, it might look easier to read if you simply swap axes. Anyhow, in the plot, the x-axis refers to the number of instances, and the y-axis depicts the runtime sorted in ascending order for each program individually. Best refers to the virtual best configuration. Virtual best configuration is the virtual program that we obtain from taking the union over the solved instances by all programs and keeping the instance with the best solved runtime. Static RootClique, we tested various variants. The largest clique, abbreviated by LQ, the largest clique including neighbors, abbreviated by LQ plus N, the largest clique excluding twins, abbreviated by LQ minus T, the largest K-hyperclique, abbreviated by KHI, the clique with the largest number of used hyperedges, abbreviated by LUH. Now let's take a look on the actual results. The FraSMT alone solves 1,300 instances. When we extend FraSMT with RootClique and the LQ plus N, so largest clique including neighbors, we solve about 1,450 instances. The next variants, so LUH, largest clique with number of used hyperedges, LQ, so largest clique, and largest clique excluding the twins, are very close together, and the best configuration there then is the K-hyperclique, so the largest K-hyperclique variant, which solves the most instances, a little more than 1,550 instances. And the virtual best configuration solves about 1,700 instances. When we now take a look on all configurations, we observe that the best configuration is with the SMT solver Z3, then static LexTopsort, static RootClique with the largest clique excluding twins, and we can actually even improve this by using another SMT solver on top, so a combination of Z3 and OptimatSat, where the solvers are used domain dependent, depending on the origin of the instances, and then we obtain a configuration that solves 1,657 instances. The virtual best configuration solves even 1,706 instances. When we compare this with the well-performing solver Triangulator MSC, so Triangulator solves about 1,500 instances on our instance set. In contrast, we solve about 100 instances more. Take a look on the scatter plots comparing the runtimes of instances one by one for our best configuration with the best dynamic symmetry breaking method on the left and with the worst dynamic configuration. The results seem to be rather bad for the dynamic variants of symmetry breaking. We're not really surprised that this is the case if one considers that the encoding size of dynamic LexTopsort is cubic and that for RootClique the encoding is quadratic. From the scatter plot we can see that both dynamic variants show that while FraSMT Z3 OptimatSat performs better on plenty of instances, there are still instances on the bottom left of the plots where the dynamic variants are faster. Further, some instances on the bottom right of both plots cannot be solved by the static version, which however can be solved by the dynamic variants. Let me quickly conclude. We introduced symmetry breaking for fractional hypertree decompositions and fractional hypertree width, and the approach where one computes it with SMT-based methods. The idea immediately applies to other width parameters and in particular Treewidth. The static versions of RootClique and LexTopsort work quite well together, and overall the static version usually outperforms the dynamic one, but in some cases it's actually worth to use the dynamic version. The combination of SMT solvers V3 and OptimatSat reached the virtually best configuration. What's up for future work? Well, we're interested in practical solving, in particular the counting problem for number CSP and the sum of products, and to consider more in the context of other measurements such as backsize and domain size. FraSMT is available online and you can download it for free under the GPL license from GitHub.